Hi, this video lesson is intended as a review. It is strictly for students who have already learned how to solve linear systems that have three variables. If you haven't learned this before, then I suggest you look at my longer and more detailed video that I also have available on YouTube. But this would be for somebody who has learned this previously and has come back here to refresh their memories about how to do the basic steps. First of all, just a reminder of what a linear system in three variables looks like. It's going to have three equations to go with the three variables. So I often call it a 3x3 system. Now that 3x3 system may come to you not from a set of equations, but instead from a word problem or from a table. You're welcome to pause and read this if you want to, but I'm going to come back to this word problem later in the video. There are two methods that you should have learned and that I'm going to remind you about for how to solve these kinds of systems. And this video just focuses on the first of those two methods, linear combination. Separately, I'll make a review video about the substitution method. Okay, just a reminder, here's a 3x3 system, and here's how the linear combination method works. First, I'll explain it in my own words, where I say attack it step by step. And in a few slides, I'll show you how the textbook, or our textbook, explains how to do it. Attacking it step by step, I mean, first of all, reduce this 3x3 system down to a 2x2 system. You'll see how in a few minutes. Once you've done that, once you've got it down to a 2x2, apply the rules that you've learned for 2x2 systems to solve that further down so that you just have the value for one of the variables. And then once you do that, plug that value back in and chug, as I say. So plug and chug. I'll say that phrase throughout the year. Here's the textbook's words for this same system and the linear combination method. And here's step one. Whoops, didn't mean to do that. You're going to use the linear combination on two of the equations to eliminate one of the variables. So let's say that what you wanted to do was focus on the top two equations, and you wanted to find a way to cancel the y's. If you want to cancel the y's between these two, then you're going to have to multiply this second row by 2. And here I've written out what would happen. Notice the first row here I've simply duplicated right there, but the second row I've multiplied everything in black by 2. When you do that, you'll find that the y column cancels, and you end up with this, 7x plus 10z equals 19. Once you've done that, take two other equations, make sure that you include the equation that you haven't used yet, and do the same thing, eliminating the same variable. If you don't eliminate the same variable, this method won't work. So let's say I wanted to combine the second row with the third row. In this case, I might, in order to cancel the y's, I would have to multiply the middle or second row there by -3. And here written out is what happens. Notice this time the bottom row duplicates what's up here, but this middle row, the black values have now down here been multiplied by -3. And when I do that, like I said, once again, the y's cancel. That needs to happen. You need to make sure that this one here, this red one, and this second one here, the green one, result in a 2x2 system that has the same letters, x's and z's. The y's have been eliminated. Okay, so now I'm just going to get rid of the clutter, and I'm just going to focus on this equation and this green one down here at the bottom. Oops. And there they are. And now I've got to do a second round in order to get this from two variables down to one variable. So one way to do it would be to find a way to eliminate the x's and leave myself with the z's. To do that, I would multiply the bottom row here by 7. So then that bottom row would become -7x, like you can see, and the rest of this in blue. So now I'm going to combine the red row with the blue row. Notice the x's will cancel, and I'm going to be left with 10 and -28, so I'm going to have -18z, and 19 and -91 combine to make -72, and I'm going to find that z equals 4. Now that I've got that third variable, the next step is to plug that value back in to one of these two variable equations. So I put In this 7x plus 10z equals 19 equation, I plug 4 in for z, so now it becomes 7x plus 10 times 4 equals 19. And if you do that, you can solve for x and find that x is negative 3. Now I've got two of the three coordinates. I've got the negative 3 and the 4. All that's left to do is find the y. To find that y, all I do is plug those first two coordinates, the negative 3 and the 4, back in to any of the equations. I happened to pick the top one there. I've plugged the negative 3 in for x, the 4 in for y. 4 in for z. I solve for y, and I will find that y equals 2. And now I've got all three of the coordinates, and I've got my solution. That's the place where those three lines cross at negative 3, 2, 4. Your turn. Hit the pause button. After all, this is review, but I've still left you the three steps here. And when you come back, I'm going to show you the results. Okay, you should have found that these three equations over here cross at the point 2, negative 1, 3. If that's not what you got, come in and let's talk about it, and we'll work through the problem together. But as I say, this is intended for people who are simply reviewing the topic, so I would expect that I didn't need to walk you through this one in order to show you how you should have arrived at 2, negative 1, 3. Now let's talk about some possible scenarios. It's possible that you could get a false answer at any step along the way. For example, all of the letters might end up canceling out, and you might end up with two constants left and right, like these, 0 equals 7. Whenever you get something that's false, like that, 0 is never the same thing as 7, then there's no solution. On the next slide, I'm going to show you what that looks like. But it's also possible that the two values, if they're just numbers and no letters left, are going to match each other, 0 equals 0 being an example. If you get that situation, then you've got an intersection with infinite solutions, just like we talked about when we were talking about 2x2 systems. Let's see what these visually would look like. Infinitely many solutions, in this case, would be a line at the intersection of these three planes. Remember, in 3 dimensions, you're going to have planes for your equations instead of lines. No solution could happen because the three planes never cross this way, or they never cross because they're parallel. Most of the problems I'm going to give you, most of the problems that you'll work with, are going to end up crossing somewhere. And this is visually what three planes crossing might look like if they all intersect at one point. Okay, last scenario. I said I was going to come to this. I'm not going to solve this for you, though, but this is an example of a word problem. This is a nicely set up one for you because not only do you get the description here, but they've already given you the table. In order to turn this into a 3x3 system, notice that you've got these values that are totals, and so really what you have is 0.55c for comedies plus 0.65d for dramas plus 0.6a for action equals 3,405. Hit the pause button, make sure you understand what I'm talking about here with this word problem, but I would expect you to be able to solve a word problem like this. That's the end of this lesson, and I'll talk about the substitution method in a separate video.